Thank you very much for that introduction. I've just proven that you cannot fill a lecture hall by talking about standards. So, okay. This talk will be about VirtIO. I'll talk a little bit about the motivation for doing VirtIO and a little bit about the motivation for doing a standard. And then we'll go through some of the history. But the core of this will basically be a laundry list of changes that we've made in the 1.0 standard. That means I'm going to have to talk fairly fast, because when I put them all together, I realized there's a little bit more than we'd originally intended in that. So we go through those changes, and then there'll be a summary, and hopefully at the end we'll have 5 minutes for questions, but you're welcome to interrupt at any time and ask a question or heckle. Okay, motivation. Basically there are differences between a real physical device and a device in a virtualized system. And it comes down to pretty much the fact that with real hardware, you poke it, it does work, but you don't pay for that work. So register accesses on real hardware are relatively quick. But memory access, if it needs to suck something out of your memory, it has to set up DMA. So there's a latency involved in that. When you're inside a guest in a virtualized system, the host that's emulating your device, for example, or pretending to be your device, those accesses, when you hit a register on your device, tend to be fairly slow. In a lot of cases, they'll cause an exit. So the whole guest will basically pack up, the host will run for a while, and the guest will come back. So that becomes quite expensive. But memory accesses, it can just access your memory as fast as you can. So there's no latency involved in memory accesses. So different trade-offs eventually lead everyone to implementing paravirtual drivers, or paravirtual devices. So in a nutshell, that's the motivation for paravirtualization. So basically not emulating hardware directly, but doing something special. Now, this was my argument for when I wrote NAT too. If you're going to do something that's horrible, try to do it well. I came to regret that decision, but I'm sure I've learned a lot since then. So let's make them not suck. And this language here, anything in italics like this, is actually a quote from the standard document itself. What we want is something that is straightforward, obviously efficient, standard, and extensible. So straightforward means, for example, that a device should build on existing buses. It should be generally PCI. Everyone expects in their machine to have PCI devices. So might as well present it as a PCI device. It solves a whole heap of already solved problems, like how do I find what devices are and how do I tell them apart, all that stuff. There's a whole very thick standard on that stuff. Let's use it. Let's not create some boutique hypervisor bus. I'm not going to mention any names. Oops. But there's also MMIO, an alternate bus in the standard, which is basically designed for embedded systems. It's not really a bus at all. It's just basically a page of registers. And generally, it's either the device tree is what informs the guest what it has, or even on the kernel command line in Linux, you can do it. And for the S390 guys, there's the S390 folks have the CCW transport, which is another thing that's much more compatible with what they do, because they traditionally don't support PCI. So straightforward also means that these things should look like normal devices. You know, you poke the registers, they interrupt you when stuff's going to happen. Straightforward. Okay. Efficient. In this case, that means batching possibly encouraged. You shouldn't have to poke a whole heap of registers to do stuff. It should pretty much be able to batch up operations where possible. Obviously, it means you support interrupt suppression by the driver. So the driver can say, look, don't bother me for a while, because taking interrupts is something that you basically, while you need to do it, you obviously need to be able to suppress it in some way. And notification suppression by the device. So the device needs to say, look, don't hit my registers and force an exit, because don't worry, I'm on it, I'm doing stuff. So that's the basic way you get efficiency. Standard. Well, obviously, if you're writing a standard, you want it to be standard. That's a little bit tautological. But in this case, it goes a bit further. When you look at what people have done in this space before, they have firstly considered only how they'll implement it on their hypervisor and come up with a boutique solution for their hypervisor and expected every operating system on the planet to implement whatever crazy idea that they came up with. But also, they tended to use different mechanisms for the block device that they were implementing, and the network device they were implementing, and the console device they were implementing, and the et cetera, et cetera. VirtIO devices actually share a ring buffer and descriptor mechanism, and that's standard. Whether it's a network device or a GL virtualization thingy or whatever crazy stuff you're doing, it will have this ring buffer and descriptor mechanism. And we call that a VirtQ, and this is another quote. And a VirtQ is basically, you put descriptors in that can basically be scatter-gather lists of this memory over here, this memory over here, etc. And the device consumes them in some way and tells you when it's finished with them. And we use that mechanism for all our devices. Now, it's called a queue, even though it's not technically a queue, because it can be evaluated out of order. But for most devices, you want it in order. A block device is the obvious exception. It needs to be able to service requests out of order, otherwise you're forcing a huge performance problem on yourself. But for network devices, they're going to be in order. Console devices, you hope they're in order, etc. Okay, but standard also means that the same devices operate on top of different transports. So net, block, SCSI, console, whatever it is you've got, balloon device, all use the same VirtIO infrastructure. So use these VirtQs I talked about. We use feature bits, which we'll mention in a moment. You have a standard config space for it to publish stuff to you. And you use that whatever bus you're on. So all of them share that VirtIO infrastructure on top of whatever bus you happen to choose. Now, we tend to talk about this from the point of view of the driver author, because more people are going to be writing drivers than are going to be writing hypervisors, despite the trend recently for everyone to write their own hypervisor. But of course, this structure is mirrored on the other side. They will also have their PCI bus implementation, and they will also have their VirtQs implementation from the other side, and their network device and their block device, etc. So the structure applies both ways. Extensible. In this case, we offer a bit set of features. And basically, the device says, here's all the stuff I support, and the driver says, here's the subset that I understand. This gives you both forwards and backwards compatibility. So crazy new device will support all these feature bits. Old driver will go, I understand that one, and that's it. So in real silicon, what tends to happen is eventually you go, legacy's too hard, we're going to release a 2.0 version, and everybody has to update their drivers. This is software. We should be able to do slightly better than that. So this is an extensibility mechanism that's actually served us remarkably well so far. So that's the motivation, and that's what we have. History. This is what it looks like. And I actually went back through the Git history to look at some of these. Git commits are not always reflective of when the work happened, but the kernel implementation of this, VirtIO PCI and also VirtIO lguest. So there's another bus that I didn't mention there because it's not in the spec, and that is the lguest bus, which is basically an array of descriptors. That went in 2007 in the kernel, labeled experimental, so of course no one was ever going to use it in production. The Qemu PCI implementation merged into the main Qemu tree actually a year later in 2008. It was obviously floating around before that. And that same year, the S390 people took basically what I'd done for lguest and made a variant for the S390 platform. So they produced their own custom bus. It was the year after that we decided that PCI was where the action was. So we were going to create an actual spec. Nominally independent of the implementation in Qemu and implementation in Linux, we'd produce a spec that would give you everything you need to know to implement something compatible. And it was focusing on PCI, so it was called VirtIO PCI draft spec. And I did that in Lix because I just like to confuse everyone by using different technologies all over the place. It was an interesting choice. And it was also the year that VirtualBox 3.1 came out, and that supported VirtIO Net. So we had our first completely independent, I only heard about when someone told me about it, implementation of VirtIO when they supported VirtIO Net. Things roll along for a few years. 2011, we got the MMIO bus merged into Linux, and that's the embedded bus where you don't have PCI and you just have a few descriptors that describe what devices you've got. So bus is a little bit of an overstatement. The year later, the S390 people actually figured that the really crappy implementation I'd written for lguest that they had copied was in fact a terrible, terrible idea, and came up with a real bus, the CCW bus support, which is much more S390-like. So much so I have trouble reading that part of the spec, but it has S390-like words in there. So, and I had hoped to say that 2014 FreeBSD 10.0 would be released. It isn't quite. It's been pushed back again. January 14th is the current due date. But something really exciting happened in FreeBSD 10. They implemented bhyve, which is legacy-free FreeBSD guest running on FreeBSD host, basically. And bhyve uses all VirtIO for all their I/O. Somebody told me about it and I took a look and went, wow, they've independently implemented all this. And so we've dragged them into the standards process as well, because that's actually really cute. So FreeBSD 10 will be VirtIO out of the box for bhyve, which is great. Now, in 2012 there, a strange thing happened. This is actually from a Google Plus post, which OHAD gave me permission to repost. The Galaxy Nexus device actually uses VirtIO to talk to the, effectively, AMP system, so the other chips on the machine. They actually said, hey, let's use VirtIO, VirtQs and everything to communicate with these. And they came up with a method called rpmessage. You can see the kernel post there. It's now in the kernel. And so they've taken the similar idea that you've got this guest and host, and the host can view all the guest's memory, but not necessarily vice versa. How do they communicate efficiently? It's mapped straight across to a very similar problem that they have. And so they use VirtIO in these devices that we all have in our pockets. Well, hopefully most of us have in our pockets. So that was kind of cool and very, very random that came out. But the real funny thing that happened in 2012 that's relevant to this talk was an email that I got from Helen, a lawyer at ARM, who said they liked VirtIO, they really wanted to use it for their fast models. So ARM don't actually fab chips, they do designs, and other people, their partners fab all the chips. If you want to do development, ARM give you an emulator, basically, they call a fast model. And you use that to do all your development, and hopefully when the hardware comes along, it all works great. And they thought, hey, it would be really good to have a decent I/O system for this, rather than emulating whatever it is they're doing at the moment. We should use VirtIO, said one of the engineers, and they went, great. This email followed with, so what are the IP licensing rules around the VirtIO spec? My answer, of course, was it's basically a glorified blog post. You break it, you get to keep both pieces. They went away after that, so that was good. About 3 weeks later, I got an email, confidential internal email from someone in IBM I had never heard of before, because they had figured out that I worked for IBM, and therefore IBM obviously knew what I was doing, and they reached into the organization, and the organization reached through to me and said, what is the IP issues around the approval that you got for releasing the spec? So basically, if we think of the spec, and the draft spec was really a white paper, there is, I have learned, a process for publishing a white paper in IBM, and it's not that. Okay. Yeah. To be completely honest, I'm actually not sure what it is. But it was made quite clear to me in a number of long meetings that it is not that. So, you know what I say? Time for a proper standard. So one solution to this, the standard solution to these kind of IP issues of who's sharing what and everything else is you make it a standard. They have all that infrastructure in place, and everyone agrees what the IP licensing or lack of licensing or whatever it is, and everyone's happy with it. So that was really the push to do a standard, because it made it obvious that increasingly, the barriers to VirtIO adoption were not technical, they were at this political and legal side. So it was time to step up. When you've got larger enterprises, they really need this help in order to use your stuff. So, and that importantly makes, the other thing about a standard is it does draw people. Nobody else is trying to do a standard here. Nobody else is trying to create something that works across all operating systems and all hypervisors. right? They're all interested in their own hypervisors. So having a standard that's actually a standard TM standard has some draw, particularly on large organizations. It's hard for them to escape the swell of knowing that there is a standard there. So it just means that it makes it an easier choice for others to follow. So this actually helps VirtIO, which hopefully helps all of us, because standards across this space do increase competition and reduce lock-in. But while we're there, why don't we try to fix up some stuff? That's right. Just, to quote from our charter, keep the good, discard the bad, and make the ugly optional. This is, yes, I wrote that bit too. Okay. Okay, but the first thing you need to do when you take something that was basically a glorified blog post and turn it into a standard is use RFC style language. I'm a big fan of this. This is in fact the last thing we did, but it should have been the first thing we did. Rather than saying, oh, the driver can check before accessing, say stuff like the driver must check, and must actually has a specific meaning, which means, flames will erupt from the keyboard if you don't follow it, I believe. But also, as I said, we tend to talk about the driver. We tend to go, okay, so we think about driver authors when we're writing the spec. But the spec really has two parts. It's for the driver authors and the device authors as well. So it has to very clearly say, the driver must do this, the device must do this. And we also had terminology. We talked a lot about host and guest. But then in the back of my mind are these crazy guys on the Nexus going, we're actually talking between different CPUs. So the language was formalized down to device and guest. And we basically went through and went, yes, let's just, just tighten up the language a bit. So that was, it actually matters, but it was a fairly minor change. Yeah, so I said we had these feature bits that you negotiate and the device presents. I think of the standards battle as being, the reason we're doing a standard is because of new users that are going to come to open up the floodgates so everyone will start using VirtIO in the future. So if you think of the graph, that means you've got more users in front of you than you have behind you. So to some extent, you can burn the users behind you for the sake of the users in front of you. Which means you have this tension between simplicity. In 10 years' time, people read the VirtIO 1 spec, and they find all this legacy crap in there. They're going, I can't believe I've got to implement all this crap. I'm just going to go do my own thing. So you want simplicity for the 1.0 people, but you still want compatibility for the poor people who are actually using your stuff today because they believed in you. Okay, so you're always going to have this tension between compatibility and simplicity. And adding a bit to say, I am compliant with the spec, which everyone must set, is actually a pretty ugly thing to do. And every driver that is compliant with the spec must accept. It's the only non-optional feature. Is definitely not simplicity for those who only care about 1.0, but obviously it makes compatibility a lot easier. So on the whole, compatibility, simplicity thing, that's more towards compatibility than simplicity. Now, while we're talking about simplicity, there were a couple of feature bits that were crap, and we just took it out. Feature bits seemed like a really good idea. The idea is you add something new, and then you can set a feature bit so everyone knows about it. It'll all be beautiful. In practice, some feature bits are documenting our bugs. The VirtIO F any layout feature bit could be called VirtIO F I actually read the damn standard feature bit. Because when you give something to the device, you give it the scatter-gather list of, here's some stuff over here, so here's some stuff over here. For example, the network device. Here's the header that tells you about the packet that I'm sending you, and the checksum information and all that stuff, metadata that you need, and here's the actual network packet. Now, a simple implementation, of course, will put one descriptor for that bit and use a second descriptor to describe the rest of the packet, etc. And the Linux implementation did that. The spec very clearly says you shouldn't rely on those boundaries. Someone should be able to either have 10 bytes here and then the rest of it here, and then use a third descriptor for the thing, or actually, as we discovered that we really wanted to do where possible, use one descriptor to cover the whole packet for short packets, including the header. Well, the Qemu implementation, which was copied from the lguest implementation, which is deliberately supposed to be minimal, just went, the first descriptor will cover the network header, right? And just have an assert that that is true. The only way to fix that is to add a feature bit. So modern QEMUs say, no, I really do actually handle any layout, and modern devices have to follow it. So that is basically a documentation of our own idiocy. And as of 1.0, that is eliminated because we say, no, you really will have read the spec this time, and we're removing the feature bit. Similarly, we had notify on empty, which turned out to be a terrible, it was actually a feature that we added because I thought we needed it, but actually it was fixing a bug, and when I fixed the bug, we didn't need the feature anymore, so it was never actually used, so we're just shuffling that under the carpet for a while. VirtQs. I'm going to get into a little bit of details about VirtQs because I think they're a kind of interesting data structure in a very boring way. So a VirtQ is basically a descriptor table. This is where it says, I've got a bit of memory over here, I've got a bit of memory over here, and a bit of memory over here. You can chain them together. It has a flags field, so address, length, flags, and a next field, which points to the next one if you're going to chain them into multiples. So you set up your descriptor table, you put your entry in, and then you put it in the available ring. You put the ID, the index of that, in the available ring, and you increment the index so they can see the next bit in the available ring. So obviously you can do multiple by bumping the index a long way. These are circular ring buffers. Okay, so the device finishes with it. It puts the ID back in the used ring and writes out the length that it actually wrote into the descriptor, which turns out to be important for some cases. Okay, so what used to happen is because we don't want the used ring on the same cache line as the available ring, I went 4096 is bigger than anyone's caches, so we'll round it up to 4096. And the device will say how big these rings are. They're all the same size, power of 2, so it'll say, it's 256 elements, the queue size. And that will, therefore, you can derive the whole size of the thing with the padding and the whole bit. That turns out to be a really bad idea because if you want to perform at networking, you might want a really, really big, actually for networking, you actually don't want a huge queue because you end up with buffer bloat issues. But for some devices, you want to go, no, I really want a massive queue of requests. And so you go, I want 32,000, which is the maximum number of descriptors you can have, which works out I need something like order of 32 contiguous pages. And so if the guest has been running for a while, when this device pops in and goes, I can't get that, it just can't drive the device. So we fix this in two ways. One, the driver for all the transports can now negotiate the size. Sometimes the device will set a maximum size, but the driver can actually say, no, I actually am only going to put in 2 descriptors because I'm OpenBIOS, for example, or core boot, and I just want to get this thing far enough to get into the real operating system. I don't want to waste more than a couple of K of memory. And in fact, those bits which are basically independent no longer have to be contiguous. So you can, even if you do have large descriptors, you no longer have to have one large chunk, you can have 3 large chunks, or 3 slightly smaller chunks. Now this introduces another axis to our compatibility simplicity, and that is flexibility or features. So we've basically gone, there's kind of compatibility in there, because you could treat this the way you did before. We haven't gained any simplicity at all, but we've got some flexibility, so we've actually left our line, and this is where that analogy whole breaks down, but we're about there. So that actually turns out to be quite important. Now, this is the most obscure part of the standard, and I left this in my talk because I wanted to cover everything we changed, and this is the most obscure thing that we changed. So I talked about the descriptor table. You say, here's all my bits of memory. In this case, we've got 5 bits of memory. So the next flag, next flag is set on 4 of them, and the next point is point down. They don't have to be contiguous in the table, but in this case, they are. So there's our 5 bits of memory. Now that means that if you're putting big buffers in, it's actually going to chew up a lot of your descriptor table. So we added a feature called VirtIO feature indirect desk. And if you support this, and everyone has since about 2009 when it was introduced, you can say, actually, indirect flag, this descriptor actually points to the table of descriptors and follow that table. So, you use less descriptors. You've got to do a dynamic memory allocation, but in some cases this wins, particularly for block devices. Really, really large requests, everyone loves them, but we have the problem of ring negotiation that if you asked, if the device said I want really huge rings, you might not get anything at all, so therefore it couldn't ask for more than about 256 anyway, so your block device performance sucked. So, indirect, awesome. So what you could do is set indirect and next, which means first go down to this table and go through that. But when that runs out, come back and follow the next chain. And that may be a direct, it could be another indirect, we could do all kinds of cool tricks here. No one ever used it. And it made it a lot harder to implement, so I just ripped it out. Whoa, yes, simplicity wins. But we kind of lost a bit of, well, theoretical compatibility sucked, but no one ever did this, so we can ignore it. And flexibility, in theory, this would allow us to do lots of multiple scatter-gather lists. We can always add that back in with another feature bit if we want. Let's not do that. Status byte formulation. So there's this, I hate bring up for this kind of stuff, and I thought, you know what? I just want a byte in every device where you set, I have seen the device, and another bit to say, I have found a driver for the device, another bit to say, the driver's good, and then a bit to say, I have failed. And I think of these as kind of attached to traffic lights on the console, so you kind of go, you know, goes red to green, and then back to red, or it'll go to, you know, whatever. So that you get some, just, if all else fails, you will get something. Now, that was supposed to be purely informative, but it turns out we have a problem now. We've got more than 32 feature bits that they're supposed to acknowledge the feature bits, right, before they start using it. But if you've got an infinite number of feature bits, how do you know when they finish acknowledging them and they're just not ignoring the rest? So we added a new status bit to say feature's OK. And so that means when you set that bit, it means I've finished feature negotiation. Everything I've accepted, that's it. It's locked in. I can't change it. But while we're there, let's just add another feature. And that is that, in theory, everyone is supposed to implement, how should I put this, RFC style, everyone should implement the complete set of feature bits. So you should handle ancient devices that only accept one or none of your features. In practice, we know people will not do that. They'll go, oh no, everyone handles indirect these days. They'll accept that feature bit. This gives them a way to do that cleanly. So when they set feature OK, you just unset it again. So they should set it and read it back. And that way the driver goes, OK, it didn't like the features that I accepted. Sure, it shouldn't ever do that, but it does give you a way of notifying and saying, I'm not going to try to drive the device because we can't agree how the device is going to work. So we kind of ratcheted that in. Again, we didn't really gain much except flexibility. This is even worse, configuration atomicity. We have this configuration area. It's great for where, you know, in a network card, it's where you put your MAC address. In block devices, it's what the size of the block device is, etc. This is actually writable by the guest as well, so it can actually push stuff in there. Tends to be a bad idea, but it is used in a couple of cases. So somebody went, the problem is if you've got multiple devices, like what if you've got a geometry information for your block device and it can change? How do you read it safely? And the answer currently is, well, hope it doesn't change, or try reading it twice and see if it did change. Neither of these apparently is, you know, really considered robust or adequate. So every transport now provides an atomicity counter. So you read the counter, you read the fields, you read the counter again. If it changed, you know something has been updated. With correct memory barriers in there, this is safe. So, and writing multi-byte fields, we talked about it. We just went, we don't do it, and we'll never create a device that requires it. Just don't go there. So we got a little bit of, it's not too bad on the simplicity front, but it is basically a bug fix. Okay. VirtIO net changes. This is what everyone cares about because everyone loves their network devices. First off, I pulled out a feature bit that was never used. So modern network cards can do GSO, basically segmentation offload. So you send the card a really big packet and it chops it up for you into little packets. It saves you round trips in your network stack. It saves you lots of talking to the driver. It's basically, you know, an aggressive, well, it's an interesting network-specific form of batching. So I thought, hey, cool, I'll add a feature bit to the spec that says we do GSO. When I came to actually implement it, and there's probably a moral here about something about not doing it in this order. See, there are specific types of GSO. There's TSO4 and TSO6 for TCP/v6. There's UFO that they may or may not do. And then there's the issue with ECN bits in TCP packets, which it may or may not support correctly. So saying I do GSO is not correct. In fact, you've got to have 4 feature bits to say what kinds it supports, at least. So we exploded this into 4 others, and this was never, ever, ever used by anyone. So out it goes. Okay, but mostly VirtIO net has stayed the same. VirtIO block, I ripped out a whole heap of stuff. VirtIO block fscsi. I had this really good idea that, hey, for our block device, we should be able to say, I want to send a SCSI command through to my block device, mainly to eject the CD, right? That was the main thing you wanted to do. You have a CD, you send a SCSI eject command. But in theory, it was a generic, you could send any SCSI command through. You can imagine what a great idea that turned out to be. No one actually used it that way, and now we have VirtIO SCSI. If you want SCSI, you know where to find it, so we took it out. I also had no idea how modern devices do barriers, so I said, I will have a barrier bit that says, when you do this write, make sure you flushed every other write before it. That was never used because that's not how the block guys roll, and now so we added a flush bit where you actually have a flush command to say flush the device. And that used to be an option, so that's now compulsory. So we ripped all those out. I also was on this kick where in the header, to keep it aligned, I had a 16-bit value, a hole. that looks kind of messy in the specs. I thought, I'll put an I/O priority field in there. And I'll define it loosely, so like, higher numbers mean higher I/O priority and lower numbers mean lower, and the rest is implementation defined up to you and everything else. With that, such a great spec and such an important feature, nobody ever used it, so we're just ripping it out. It's now called unused again. So that's all simplicity. Whole heap of stuff ripped out of VirtIO block. It is back to being a very, very simple block device. If you want anything complicated, VirtIO SCSI is where you want to be. Okay. VirtIO balloon. Does everyone know what a balloon driver is? Okay. Does everyone not know what a balloon driver is? I should ask that question. Okay. Good. Okay, there we go. Okay. And therefore, I assume that about 30% of you are asleep. Okay. This is a Zen thing, and it was actually quite a clever Zen thing. Basically, you have the concept of a balloon inside your guest. And so your guest is like this big, it's got this much memory, and you can tell the guest, please inflate the balloon. It would basically push pages into the balloon and crowd itself into the rest of memory. And the pages inside this balloon could be used by other machines on the system. So basically, it would push pages into the balloon as requested and squeeze itself into the rest of memory. And then, of course, for whatever reason it needed to expand again, it would pull pages, deflate the balloon, and re-expand it into space. So think this is a poor person's memory hot plug, basically. But despite being so trivial, it's actually amazingly effective in a lot of scenarios. So we implemented and by we I mean somebody else, implemented a balloon device spec. It uses the config space to say what balloon size it should be. Only, unlike every other part of the spec, it gets the endian wrong and says it is always little endian. So that was wrong. It also has a stats field, so the device can ask the driver, hey, what are your memory stats in the system? And it uses a U64 and a U8, U16, and they have to be crammed together. It has to be packed, because you can ask for multiple of them. So there's an alignment issue. Means that all your alignment will then be out for everything. And it also has a feature which says, please tell me before you pull a page out of the balloon. Don't just fault it in. Please tell me. That was to support a theoretical hypervisor that would require that. But the problem is that what does that theoretical hypervisor that requires that feature do if the device says, sorry, if the driver says, actually I don't accept that bit. You're like, well, I need you to. Unplug the device again. You lose it. Presumably you wanted a balloon in there for some reason. It was an optional. It was a compulsory optional feature bit, which led to all kinds of strangeness when it was appreciated. And it turned out nobody ever needed that feature bit anyway. So we did the best and simplest thing possible and ripped the VirtIO balloon. It is proposed to rip the VirtIO balloon entirely out of the spec and replace it with something that is really, really simple and doesn't have these issues. Of course, the discussion, hey, if we're writing our ideal balloon, do you know what else we could do? Has arisen, and we're going through that battle now. So at the moment, it's looking like ultimate in simplicity. It may be something else. We may be up the top of the feature triangle again, but I'm hoping for simplicity. So we're basically just not going to include it in the spec. And that doesn't mean it doesn't exist and it doesn't exist in legacy. It doesn't mean that it can't be that feature, that device number can't be reserved for people who want to implement it. But the proposal is with Working Draft 2 is it won't be in the spec. So clear that. PCI changes. I'm going to go through this pretty quickly because there's actually not many. We wanted things like the ability to negotiate the queue size, and we wanted more than 32 feature bits and all that stuff. So obviously we have to change the layout in PCI space. Now, we had an issue in PCI space where everything was in bar 0. So if you don't know PCI, you can go to sleep for a bit now. Everything was laid out in bar 0, and you had all the registers for the device and stuff that you needed to know. And then you had the driver-specific stuff. So if it was a network card, it was a network stuff. If it was a block device, it was a block stuff, whatever. Then someone added MSI, and they went, where do we put this in this continuous bar? I know, when you turn MSI on, we'll insert the fields at the end and move the device-specific ones across. And if you turn it off again, they move back. And then we thought, okay, that's ugly, but what happens when someone else adds one? Another thing they want to extend it with, are we going to have this complicated spec where you have a state machine that says if you turn this bit on, it's at this location, otherwise it's here, and multiply that by the number of, no. We decided to actually separate them out and use the PCI capability list to point out where they are, which also allows you to put them in other crazy places. So yeah, in some ways it's a little bit simpler than that whole moving thing because they're specified up front. It does allow compatibility because you can still have bar 0 there with the old style. If they access that, you go, I know what you're doing. You're a legacy driver. It also gets a little bit complicated with following the chain and stuff. Turns out that modern PCI devices, you're supposed to be able to access them even if you can't access one of the I/O bars according to the spec. So what everyone does is they put in like a magic little way of poking stuff in. And apparently this is now the norm. And so we want to be there with the cool kids. So VirtIO spec also has this backdoor way of poking through registers, which I really hate, but is in the spec. Okay. The worst one, however, is the spectre of endianness. This VirtIO is defined as guest endian because I'm brilliant. Because guest, what could be simpler? You're writing a guest driver. Don't worry about endian. The host obviously knows what endian you are, right? Because it's doing all this stuff for you anyway. Just chill, man. Don't worry about the endian. Just, write natural, be free. So it turns out simple is not the same as straightforward. Straightforward is what I expect. Simple is, doesn't have anything. And I actually said sort of presciently in the beginning that we would be straightforward. So not only does this cause an FAQ, but of course the balloon driver, as we saw, got it wrong, and we had to put this thing saying, they're always little endian despite the convention. Yes, and that bit had to go in there and it's okay. So, screw it, little endian. Little endian everywhere. Simplicity for the win. Little endian for the descriptors and the rings and the blah, blah, blah. Okay, yay! So if you're ARM or x86 little endian, there's no change. It's all beautiful. So if you're PowerPC big endian, which I have some vested interest in, you are going to end up with this conditional endian swap. Oh, hold on, you're a legacy device. That means I don't swap. Oh, you're a non-legacy device, so I actually now need to swap to the endian. It's actually not that bad on my rough, looking at the code traces and stuff. Generally, GCC will put a single branch in and you'll end up with a couple of extra branches. It's not too bad. And of course, that branch will be always predicted really, really well. So it's not that bad. PowerPC little endian, of course, it becomes a simplification because then, and PowerPC, IBM recently rediscovered that their chips can run both ways. So now they're little endian. And so that's simplification. The RMBE guys, well, it's not clear because they don't actually work at the moment on VirtIO. So if they wait long enough for the VirtIO 1.0 standards out, then they won't need to worry about legacy and they'll just always swap. It's the poor people on the S390 who really took the bullet for us on this one. And it really was them going, look, we don't want to block the standard. So we are going to just suck it up and do this thing that is deeply, deeply unnatural on S390 and speak little endian. So, yes. So actually a huge public thanks to them for doing that. One option they could have done is on S390 we're big endian and everywhere else we're little endian. But you know that they would hit every single bug imaginable over time as people made assumptions about, oh, it's little endian everywhere. Oh, yeah, I forgot about you guys again. So, in summary, we have a standard. We have a standards committee. And on Christmas Eve, you may have missed it, we released the very first public review draft. So basically you go through that and you apply comments and we are required to respond to them. We're required to record them. So there are the URLs. The PDF is nominally canonical. It's generated from the text source, which is actually probably more canonical, but the PDF, but the HTML is more readable. We have a second working draft already in the works, and that will cover any feedback we get. And there are also some missing features. One thing that missed out of the spec, and a bit more language tightening. So, are there any questions? Yes, Dave. Oh, really? Did they use? Oh, yeah, I vaguely recall that. Were they using the RP message stuff? Yeah, but RP message is the layer on top of VirtIO that they got. So yeah, there actually seems to be some traction in a really weird way. The standard effort has pretty much stayed away from that. We pulled out the RP message chapter, didn't even try to get IP approval for that because they're kind of weird. We love that they're using our stuff, but whether we want to actually go as far as to put them in a standard or whether there should be an adjunct standard or not if they want to go that path. But yeah, it actually seems to be catching on. Because people are like, well, this is actually the easiest way, and the infrastructure is already in the kernel. So yeah, thanks for that. Yep.
Once you added
Keith.
indirect tables, is
Yep.
there some reason you just didn't remove the next chain from the main grid?
Yes. Sorry. So there was a question on why, when we added indirect, why didn't we just remove the whole next chaining thing? It turns out that if you're memory constrained and you can't do that allocation, it's much better to be able to at least shove it. You know, you'll lose some performance, but you can still shove it straight in the main chain. It doesn't turn out to be that bad when you implement it, because if you don't have this whole indirect and next thing at once, then you basically start on the main table. If there's an indirect, you're only allowed one indirect. You just flip to the table they've pointed you to. You can't keep going indirect. No, that is specifically banned in the spec, and no one's seriously suggested removing it. So, any other questions? Yeah, question here. Have we had any involvement from the non-Linux commercial hypervisor people? I also took this opportunity to turn it into a standard in a public forum as an opportunity to go back around to them and say, hey, you know, are you interested? I previously, like years and years ago, reached out to both VMware and Microsoft. Informally, you know, through technical contact, didn't come up with anything. My personal feeling is that with the Zen guys sniffing around, that leaves two left, and that's VMware and Microsoft. If we get one of them, we'll get the other one. Or if we convince one of them we're going to get the other one, we might get it. So, did I say that out loud? Yeah, I mean, obviously, if one of them's got the checkbox of the VirtIO standard and the other one doesn't. But frankly, we're kind of swelling around them at this point. Every little hypervisor out there, the ones I haven't heard of, are going, well, the easiest thing I can do is implement VirtIO. And that is enough for me. If they want to come on eventually, or if they want to just lose market share because they're not coming on board, both of those options are frankly about equal to me. I mean, I would love to have their involvement, and I'm looking forward to working with them on the VirtIO 2.0 spec. Yep.
How onerous has the standards process been? Is something you recommend more?
How onerous has the standards process been? Don't do it for fun. I would definitely say that. I had hoped to have it finished 3 months ago. We've now got draft 1 out, and we've got at least one more draft, maybe 2. So it's going to stretch into middle of next year. And every time I give a due date, add 6 months, because it's always been longer.
Does that mean this year?
Yeah, sorry, this year. Yeah, phew. Yes, you can read that both ways, yes. Okay, we have one last question. Oh, but sorry, on the standards thing. The people I've been working with are all the technical people. I haven't been dealing with any like language lawyers or anything like that. So that part of the process has been really smooth. But getting up to speed on how to run a standard and interfacing with the standards crowd and stuff, that's been the time-consuming stuff.
Do you think it's actually going to be the final thing that gets done is VirtIO handling the graphics subsystems, or is there hope that that won't be the absolute last thing VirtIO manages to do?
You know, there's an interesting talk later in the week that I recommend that Dave Airley, I know, has been sweating over, and I recommend going to that and asking him that question.
And with that, thank you very much, Rusty. And